Okay, let's assume that you have a flexible, sort of like a rubber rod, uniformly charged. Let's say charge is given, Q, length is given, right? And then you bend it into a semicircle. And of course, it creates an electric field everywhere, but we want to find electric field at the center of the semicircle. Why that point? Because lots of symmetry, and calculations can be reasonably easy or reasonably complicated, because for any other point, calculations will be really, really crazy. All right? Okay, so let me draw the picture, and probably first I will write, so we have charged semicircle. Right, and what is given? The total charge and the total length. That's L capital, total length of that rod. Yeah. And now let me draw. Finally, I can use this device. Okay, it should be enough. Let me estimate the amount of space. Yeah, I think it should be enough. Okay, semicircle. This is the center. So let's call it point P. So we need to find the electric field at that point P. So let me write down. So we need to find E at the point P. Actually, as a vector, I'll probably write down. Okay, soon I will have to change my marker. So yeah, that's it, right? And of course, this is the center. Since we will have to find vectors, a vector coordinate system is a must. So we must show which is the x direction, which is the y direction. Without that, yeah, it would be very strange. Right, so let me show that this is, let's say, y, and of course this will be our x-axis. Okay, so that's the situation, and now let's discussing it. Let's start discussing. Again, like in the lecture, I told you. So right now we have only one expression, one formula, which we can use. A formula for the electric field created by point charge, nothing else. So we have to use that somehow, and that is definitely not a point charge. It's a rod. Actually, now we can call it a semicircle. Right? So, and the beginning is typical, as I told you in the lecture. Let's take infinitesimally small section of this rod. Let me take, for example, it here. So that's infinitesimally small section of the rod. Of course, it has length dl, and of course there will be some amount of charge dq. And again, I will pronounce the same words like in the lecture. What does it mean infinitesimally small from the calculus point of view? It's very simple. It means that it's smaller than anything you can think of. Again, it doesn't matter how wild your imagination is. dl will be all the time, by definition, smaller. So if it's so darn small, it means that what? It means that we can treat with extremely good approximation. We can treat it as a point charge. It's the beginning for any, when you want to set up an integration. Every time you take something small and treat it as a point object. Okay, so now maybe I will write again these words. So take dl with the amount of charge dq and treat it as a point object, point charge. Okay, so that's the beginning all the time, and I've done exactly the same in the lecture. Okay, so now we can, first of all, we can draw the contribution to the net electric field at this point from that small section dl. Right? Okay, maybe I will first draw a, how should I draw? Okay, so this. And so, of course, the electric field will be along this line. So that's the contribution dE. It's a small contribution to the net electric field at this point from that charge dq. And of course, there will be contributions from that section, that, pretty much from each section of the rod. But we took some arbitrary dl, and that's its contribution. And of course, we can write the expression for the magnitude of this electric field. Because it's a point charge, we know the expression. So of course, we can write that dE equals k times dq divided by the square of the distance from that point charge to the point P, to the point in question. Right? You see, so far steps exactly the same in the lecture. Right? So now we need to write all this in terms of what is given and a single variable of integration. Again, which variable of integration, it's difficult to tell from the very beginning, but we will just start evolving it, start diving in deeper and deeper and see what will be the best, which variable will be the best. So first, what can you say about this r small? R, it's at this distance, right? It's this, from this point to that point. And that's constant, that's the radius because it's a semicircle. Of course, radius is not given, but at some point, of course, we will express radius in terms of L, and it's simple, right? But for now, let's introduce R capital. That's not the major issue, right? So let's just use for now R capital. But again, in a few minutes, we will get rid of this R capital and use L capital. Anyway, it's constant, right? So now we know this. Now we just need to write dq in terms of what is given. dq. And now we need to recall again that slide in the lecture before I started discussing the example, integration example. You remember those linear charge density, surface charge density, volume charge density. Again, we need to recall that. And again, look, the object the object physically object is basically two-dimensional, right? Half a circle, it's a two-dimensional object. But distribution of charge is still one-dimensional. Charges are distributed over this basically line, right? Okay, not a straight line, but semicircle. Again, object is two-dimensional, but the charge distribution is linear. So we need to use linear charge density lambda. Of course, if we had a half of a disk, uniformly charged, of course, we would have to use surface charge density. But here, charge is distributed over a curved line. It's one-dimensional. So I will use lambda, linear charge density. Again, that slide from the lecture. And in order to find the amount of charge in this small section, we need to multiply it by dl. Right. And so now, it looks like we introduced the variable of integration L. I don't know if it's good or not, we will see. But next step, we need to write down the expression for the linear charge density. We should be able to find it. Because total charge is given, and we know the total length over which this charge is uniformly distributed. So we just need to take total charge and divide it by the total length. It's like in that slide we were discussing, right? If you have a rod, charge Q is distributed uniformly, and if you know the length, just take the total charge divided by the total length. The same with mass. Mass density, charge density. What a big difference, right? So I can write this as Q divided by L. So it's a linear charge density. Maybe I should emphasize that this is linear charge density. All right, n times dl. All right. Okay, so now it looks like yeah, we wrote dq in terms of q is given, L is given, and the variable of integration L. But of course, okay, in the integral it will be dl. Now the next step, maybe like in 5-10 minutes, we will sooner or later we will realize eventually that L is not the best variable of integration, and of course dl is an integral. So let's switch, and again in maybe in 5-10 minutes you will see why. Let's switch from dl. Let's introduce the new variable of integration, and let's introduce this angle. Right, you know what, let me remove this r. First, let me show this angle. Let's introduce this angle theta. And now let me bring back that r. Right, probably I will show it here. Right. Let's introduce that angle theta. Because again, in a few minutes you will see why I'm sort of jumping ahead and said, let's at this point switch variable of integration. And so we need to connect dl with d theta. Again, let's see on the picture where d theta is. So this is dl. Of course, d theta must be an angle which supports this dl. It's at this. If I draw this line, so this will be d theta, the angle, this infinitesimally small angle d theta, which supports that arc length dl. Right? So that is theta, and that is d theta. It's a typical steps in integrations. For those of you who are familiar with integration, of course, it's banal. Of course, for those of you who are still learning, right, might be challenging. But we need to be exposed. You need to be exposed to that. Right. Okay, so now, who knows or maybe remembers how to connect this d theta and that dl? Usually at this point, students don't remember this, right? So I have to refresh. We have to refresh the how to connect them. Right. So let me first write introduce. Oops, it's a mess. Introduce d theta instead of dl. Okay, right? And now let's connect them. You remember definition of radians. How did we introduce radians? Okay, I will use maybe my circle.
A unit circle?
For unit circle, okay, yeah, you're moving in the right direction. You're moving in the absolutely right direction. Definition of radians. Again, usually students don't remember that, right? All right, and I have to refresh that. If we take, or maybe I will use this. Right. No, it doesn't work. I will use by hand.
Is this like to say 2 pi is 360 degrees, like that?
Not exactly. 2 pi 360 degrees will allow you to connect degrees and radians.
Okay.
But we need to connect r, this r, and or actually dl and the d theta, or theta and arc length. Okay, so let's refresh. So let's assume that, okay, so we have a circle of radius r, and let's assume that we have this angle theta. Of course, you can use you can use degrees to define that define that angle, or we can use radians. What is angle? This angle in radians by definition. So of course, this radius is r. This is the arc length subtended by that angle, right? So let's say L. So by definition, angle theta in radians, by definition, 3 lines, it's the ratio of that arc length divided by the radius of the circle. That's how we introduce angle in radians. by definition, 3 lines. That's why I have 3 lines. Again, okay, we can frame it. So, and now you can see, so how we can connect, how can we connect dl with d theta? Easily, right? So from here, of course, I can write that L equals r theta. And then, of course, since r is constant, I can write that dl equals r d theta. That's the transition. Transition.
Is it just like R is S for arc length?
No, r, it's a radius of this circle.
I'm sorry, L is arc length.
L is the arc length, of course. L is the arc length, you see? Right.
I think my calculus professor used to use an S for that.
Okay, it depends, right? Different books use different. Of course, you can use S, you can L. It's a potato, right? It's basically the same, right? Different books use different notations. So S and L, yeah, they're interchangeable, basically. Of course, R is constant because it's a circle. Okay, so that's what we need. That's what we need over here. All right? So now let me write back to our problem. Right? So now let me write dE. So now we know how to write dl in terms of theta. And so now let's put it all back to dE. So dE equals, right, so k dq is that it's a q over L. Instead of dl, we have r d theta. Instead of dl, we have r d theta, and divided by r squared. R squared, it's a capital R, right? Of course, one r can be canceled, right? And as a result, we're getting k q d theta divided by r times L. Okay. So now, of course, r is not given. L is given. So we need to get rid of r and write it in terms of L, right? Of course, we could have done it from the very beginning, but I felt like it's better to, after we went through these transitions, right? So now let's replace r. Right. So L, it's the length of semicircle. How else can we write the length of a semicircle? Pi times r. The total circumference is 2 pi r. But since we have semicircle, it's just pi r. So that's how we can connect it, right? Connect them. So it's a pi r. Let me emphasize. So it's just a semicircle. Right. Of course, so r equals L divided by pi. Right, so let's plug it, and we will have expression for the magnitude of the electric field. So we'll plug it over here. So it will be k q d theta. Of course, this pi will go upstairs immediately. Let me move pi upstairs. Oh no, let's do it step by step. Q d theta and L over pi times L. Right. So it will be k pi q d theta divided by L squared. Whew. Okay, so now that's the magnitude of this electric field, length. But again, now we need to be careful. You cannot just, of course, you need to integrate, but you cannot just grab that formula and start integrating over the whole semicircle, because this is the vector quantity. According to the calculus, what you're supposed to do at this point, you're supposed to find x component of this, or y component, and then integrate them all. Integrate them, right? So of course, at this point now you need to find E. You know what? Probably I don't have enough space over there. So of course, electric field will be integral of dEy, right? So we'll have to find electric y component of the electric field and then integrate. But let's try to skip this integration because we have plenty of symmetry and we might be able to skip this integration. All right, so let's use symmetry to skip this integration, to skip this. What do I mean by this using symmetry? Look, we have this section dl on the upper part of the semicircle. But at the same time, I can find symmetrically position dl on this side with the same dl, the same dq. And of course, this is going to create similar electric field, but pointing that way. And now let's look at the components, y and x components of both these fields. So y component will be here, right? X component will be here. Now, about this red, of course, the x component there, y component is here. Now look, what happens to the y components of this red and blue y components? They're the same in magnitude, but in the opposite directions. They cancel each other, brutally cancel each other. So during your integration, it doesn't matter which section you can find in the upper part. There will be a section in the lower part with the opposite y contribution. So every time y components are going to cancel each other. So this integral will be 0. Of course, I can see it graphically because of the symmetry, but if you said, but you can say, of course, I don't believe your picture, right? I don't believe your justifications, right? Okay, not a big deal. Write down this integral explicitly, and you will end up with 0 mathematically. So let's just skip it because we can see from the picture that that integral will be 0 anyway, right? Right, so we can write that y component of the electric field eventually will be 0 anyway. So what's left? X components, of course, they don't cancel each other. X components survive, and they will give us something. So let's find x component of this electric field and integrate it. So here we cannot skip. All right. So of course, only x component survives. Right. Okay. So now let's find x component of this electric field. So we need to, let me write. So this is the x component, right? So this is dx, dex, right? You see this one, right? So this is our dE. And now we need to find this horizontal component. We introduced this angle theta. Exactly the same theta angle is over here, right? So it's this theta, you see, and here theta. Okay, now lots of red. So if we need to find this component which is opposite to the chosen angle, so this is theta, this is theta, this is theta. So we just need to multiply by sine. Okay, let me finish, guys, this problem, couple of minutes. So we need to multiply it by sine of angle theta. So you see now that's why we moved at this point from L to theta, because I knew from the very beginning that this sine theta will pop up. So that's the reason why I moved from L to theta. Okay, so now basically we just need to start integrating. So let me write this dx. Instead of dE, I will write this. So it will be integral of out of k pi q L squared sine theta d theta. So I just plug dE instead of this dE and multiply by sine, and of course integration. Limits of integration. You start from here because you see we measure angle theta from the vertical, from the positive y direction. So when you are here, angle theta is 0. So the lower limit is 0. All right. And then when you get to the lower part, to this part, to the end of the rod, you are at this point and the angle is pi. So 0 from 0 to pi. So that's the integral. So all these are constants. So we can take them outside. And then we have integral of sine. Right. So it will be k pi q over L squared and integral of sine theta d theta from 0 to pi. This is a trivial integral. Integral of sine is minus cosine. So it's a k pi theta over L squared and minus cosine theta with limits from 0 to pi, minus cosine theta. Okay, I'm running out of space here. All right, so it will be minus k pi q over L squared. And cosine of pi, upper limit cosine of pi is minus 1. And then minus cosine of 0 is 1. So as a result, you're getting the minuses will disappear. And we're getting the answer and the end of the class. Right, so 2k pi q over L squared. So that's the answer.